So Shruti defined what is called weak topology, weak star topology. We will discuss more on that in this class. Okay. So what is weak topology? So if X is a non-linear space, X is a non-linear space, and so in weak topology, so X star is its dual. Then weak topology is the smallest topology which makes all those bounded linear functions which are already continuous with respect to norm. Okay, they are all we define boundedness which is equivalent to continuity of the linear functionals. But then that's a slightly that's a bigger topology. You want to consider a topology which is smaller than that, and that is what is called weak topology, which is the biggest, smallest topology. With respect to which, which makes smallest topology, which makes all functionals in X are continuous. Okay. So this topology, you can directly, you can write down all the open sets. The open sets, you can write down the base for this topology. Base, this is a general procedure. If you have any set and if you have a collection of functions, then you can describe the smallest topology which makes all those functions continuous. And it is the prescription is precisely the following. So then the weak topology is just B equal to, this is the base. This is not the topology, is a collection of open set. Base means you have a collection of base sets whose arbitrary union will generate the topology. Okay. So this is all those phi1. So I think base means you take the, no, base is this is base. I don't remember what is called base in topology, but this is how the topology is described like this. The weak topology equal to arbitrary union of all these sets. Phi1 inverse U1 intersection Phi2 inverse U2 up to some Phi n intersection, Phi n inverse Un, Phi1 inverse U1, the inverse image of some open sets in complex numbers. Contingency. So you take the inverse image of some open set in complex plane using some linear functional, collection of linear functional, and then take the finite intersection of that. That will form what is called a base or whatever. Then you take arbitrary union of those sets, and that is what will form the weak topology. So the topology is explicitly given by this. Okay. So in particular, a set, say G contained in X is open. A set is open if the given any point is open if given any A in G, there exists a B equal to Phi1 inverse U1 intersection up to Phi n inverse Un, which contains A is in B and B is contained in G. Okay. Given any A, there should be a base open set which should contain that A, and it should be completely contained in G. So this is what the definition of openness. So, okay. So, but then if you have A is in B, implies Phi1 or Phi I of A is in Ui for all I. Okay. But since Ua is open, there exists epsilon I. There exists epsilon I such that B of Phi I A epsilon I is contained in UI. Okay, and you can take epsilon equal to minimum of all this epsilon 1 up to epsilon n. So if you consider this, if you, I mean, whatever we have discussed, these things will imply that G is open if for any A in G, there exists a phi1 up to phi n. There exists a phi1 up to phi n in X star, and epsilon greater than 0, such that A is in phi I intersection of I equal to 1 to n, phi I inverse of phi I A epsilon. That's right, phi I A epsilon. That's all, which is contained in G. Okay. I have just written the definition of open set, and I have just, I mean, using the linear, I mean, using whatever the given information, I have just written it like this. So,
Sir,
yeah.
It is phi inverse of ball of phi is.
One second. This, I mean, are you able to see everything? I mean, here this is blocking. One second. Let me just move this here. Can you just see everything? Okay. So ask me. Tell me.
Yeah. So last line phi inverse ball of phi is.
Correct. It's ball up. Correct. Correct. Exactly. It's a ball. Right. It's a ball up there. Right. Okay. Yeah. It's a ball up there. So I want to define a neighborhood. So this is a neighborhood. So let me use this notation. So let B. So A for A in, this is like a neighborhood around any point A. Okay. So for A in X, define B A phi1 up to phi n and epsilon. Something precise like, so that intersection, whatever I have just, you can just write it like this. All those X in X, such that phi I X minus phi I A is less than epsilon for all I. Okay. Okay. This is like an open ball for, this is like an open neighborhood. I mean, usually in a metric space, an open ball will be given by a point A and epsilon, and then positive number epsilon. But here you need some phi1 up to phi n also. Okay. So this is a neighborhood around A. Okay. And if any set is open, if and only there exists a neighborhood around that which is completely contained. So the reason for writing all these things is I want to use the following proposition. I want to say that the weak topology is something which is some smaller topology than the strong topology. So for that, so I want to prove the following proposition. Proposition is any, so let X be infinite dimensional. We have to assume X is infinite dimensional. X is infinite dimensional. Then any weak open set is unbounded. Okay. So this proves that if it is infinite dimensional, then the weak topology is actually weaker than the norm topology. Norm topology, you have bounded open balls. Okay, you have open balls like this, B of some x naught epsilon, which is all those x such that norm of x minus x naught is less than epsilon, not less than or equal to, less than epsilon. Okay, and such set, this is a norm open set, and such set cannot be weakly open. Okay, So clearly, weak topology is weaker than the norm topology. So we want to prove this proposition. In infinite dimensional non-linear space, any weak open set is unbounded. I mean, it's unbounded in norm. Okay. I mean, when we say bounded or unbounded, we have to, I mean, we need a metric. So that is the norm. Okay. Unbounded in norm. So to prove this, I need the following lemma. So X is infinite dimensional. Okay. And let phi1 up to phi n or in X star. Then there exists a X in X such that phi X equals 0 for all I. Okay. So this is actually, you can prove it in many ways, but there is. So we have some collection of linear functionals and it's an infinite dimensional. So I mean, whatever you do, I mean, if you take the range of all those things, I mean, the range of linear functional is one dimensional. And if you take a collection, it can be at most n dimensional and you will have something extra space. I mean, you will have some vector where, I mean, even if you take the intersection of the kernel or something, you will have some, let me just do it. So let phi1 up to phi n be contained in, phi m is contained in phi1 up to phi n and linearly independent. I mean, that set may not be linearly independent, so I'm taking a linearly independent subset of that. Okay. And since X is infinite dimensional, X star is also infinite dimensional. I mean, if that is not the case, X star is finite dimensional, X double star will be also finite dimensional. That will mean X is finite dimensional, so which is not possible. So because of that, X star is infinite dimensional. Now choose a phi. Maybe I'll use the same notation. Phi in X star, which is linearly independent of this, which is possible because it's infinite dimensional. Okay. Phi m. I mean, initially I had some n linear functional. I've chosen a linearly independent subset of that. Then I have adding one more to that. Okay. Now you define the map phi from X to C m plus 1, okay, by phi of X equal to, it's a m plus 1 tuple. So phi 1 X, phi 2 X up to phi mx and then phi of X. Okay. So the claim is, so I'm defining this. The claim is this phi of X, this phi is onto. So suppose phi is not onto. Onto. Then there exists a, alpha 1 up to alpha n plus 1. I mean, you can use inner product and other thing. I mean, it's just a finite dimensional space, which is orthogonal to range of phi. Okay. Or you can take what's happening here. Where am I writing this? Name of the file. That it's a new file. I don't know. Good. I don't know when this happened. I opened a new file. I don't know why I have all these things here. It's something I was teaching my son, and it's all here. Okay. Physics, actually. So, um, okay, something has happened. Anyway, I will allow space. Okay. Okay. So yeah, suppose if it is not on 2, then there exists a vector in Cm plus 1, alpha 1 up to alpha m plus 1, which is orthogonal to range of phi. Okay. And that will imply, what does it mean? You just write what does it mean? This means that alpha 1 times, I mean, the range is like this: alpha 1 times phi1x plus up to alpha m plus 1 times phi alpha m times phi mx plus alpha m plus 1 times phi x equals 0. Okay. But since phi i's and phi, they are linearly independent, alpha a has to be 0 for all. Okay. So this implies phi is on 2. So it's clear, phi is on 2. Okay. So since phi is on 2, there exists a x in x such that phi of x equal to 0, 0, 0, and 1 in the last place. I mean, that is phi I of x equals 0 for all I, and phi of x is not equal to 0. So this implies x is not equal to 0 because phi of x is not equal to 0, and the initially whatever we had phi x, because that is just linear combination of these things. Okay, these are because this is linearly independent. Phi x equal to 0 for all I. Maybe I should have used a different indexing. That doesn't matter. Okay. So this is our initial lemma. We are given a n set of, I mean, finite set of linear functionals. Then there exists a x which vanishes for all, which is in the kernel of all those things, which is in the intersection of the kernel of all those px. Okay. Okay. Now proof of the proposition. So the proof of the proposition says that if you have any weak neighborhood, then it is unbounded. So it's enough if we prove that any weak neighborhood is unbounded, because any weak neighborhood is contained in any weak neighborhood. So let u equal to consider, I mean, it's enough to prove whatever the p of a phi1 up to phi n and epsilon is unbounded. But that is clear. Choose x in x not equal to 0, and phi a x equal to 0. Okay. Then, sorry, I choose this a. Okay, a is 0. Why is this enough? I will tell you. Then phi a x equal to 0. So phi a x is of course equal to 0, which is less than epsilon. So this implies phi x, I mean, it's not just that. If you can take any k times phi times kx, which is also equal to 0, okay, because it's linear functional for all k, in for all k positive, let's say. Okay. This implies kx is in that b, okay, for all k positive. So this implies that is bounded, that is unbounded. Sorry. And now, if you want to talk about any b a phi1 up to phi n epsilon, but that is just a plus b 0 phi1 up to phi n epsilon. This is what is called locally convex topology. I mean, you can shift I mean, every neighborhood is a shift of translate of a neighborhood around zero. Okay, it's clear. This is just a plus something. I mean, this just means any vector here is a, any x there is a. I mean, it will look like a plus x. Okay, for x something here. It's just clear. Okay. So because of this, any weak neighborhood is unbounded when x is infinite dimensional. So next, weak star topology. This also was defined by her. So I will just describe the neighborhood. The neighborhood is given by weak star neighborhoods are given by some element phi. So this is a topology and the dual space. Weak star topology is a topology and dual space. Okay, B of phi. So x star be a dual space maybe. Let x star be a dual space. X is a non-linear space and x star is a dual space. And the weak star topology is defined on x star, on a dual space. So a weak neighborhood, a weak star neighborhood of phi is described by some b of phi up to x1 up to xn and an epsilon. I mean, the same way which I described earlier, you can write it. I mean, this is an exercise, okay? You can go through the same argument and it will look like this. So all those, maybe I call it phi naught. So all those phi such that phi of xi minus phi naught of xi is less than epsilon for all I. So this is a weak star neighborhood. And I mean, if you want to work, you can do the same thing with that. So the point is, what do you want to say next? So Shruti proved that any open ball, any closed ball is weak star compact. Okay. Of course, weak topology and weak star topology coincide when the space is reflexive, then they are same. Otherwise, there is no reason there. I mean, there is no reason that they are same. And in fact, the balls will not be compact in weak topology. It's only weak star compact. For example, so to differentiate weak topology and weak star topology, we have to consider non-reflexive space. Till now, we know only one we have studied one non-reflexive space, which is L1. Okay. And so let us consider this L1. So C0 is space of all sequence converging to zero. Okay. Sequence converging to zero. And L1 is, of course, the non-summable sequence. I mean, absolutely summable sequences. L1, and you know what is L1. And L infinity is all bounded sequences. This is summable sequences. So this is bounded sequence. And you know that C0 star equal to L1 and L1 star equal to L infinity. Okay. So I want to say that the weak topology and weak star topology are completely different on L1. So one thing is notice is consider this En. So En is a sequence. This 1, sorry, not 1, 0. 0, 0, 0, 0, 1 at the nth place. Okay. This sequence, I mean, just the basis sequence. So then this En, consider that as a sequence containing n equal to 1 to infinity. So this is contained in L1. Okay. So this is a sequence which is 1 at the nth place and 0 everywhere else. Okay. This En is an element in L1. Okay. And Dn is a now you consider the sequence of this En in L1. Then the En converges in weak star topology to 0. But En does not converge to 0 in weak topology. This shows something more. This En is, En has norm of En equal to 1. Okay, En is in the unit ball. Okay, and En in fact does not have any converging subsequence. Incidentally, I will give an assignment which will show that if you have a separable non-linear space, then the unit ball is weak star. Unit ball which is weak star compact is actually metrizable. There exists a metric which generates the topology. And topology comes from a metric. Okay. So because of that, the compactness is made. It's sequentially compact. Okay, the compactness is actually sequentially. If the space is separable, then the unit ball is sequentially compact. So every sequence will have a convergent subsequence. Okay, but then this shows that this En does not have any convergent subsequence. We will discuss this. So this will imply that the unit ball of L1 is not weakly compact. It is weak star compact, that is given by Banach-Alaoglu theorem, but it is not weak star compact. That's what this shows. So why En converges to 0 in the weak star topology? Converging in the weak star topology, so En converges to 0 in weak star topology. The reason is, what does it mean by converging to 0? If you have any, in the pre-dual, the C0 star, if you have any phi in C0, okay, then En of phi, En of phi, I can write it as phi of even if you want. Okay, what is this En of phi? En acting on phi is nothing but, or let me take a sequence in that. Okay, let Xn be a sequence contained in C0. Okay, then this En acting on that Xn. En acting on this, I should write Xk. The En is there, so Xk. En acting on the sequence Xk. Xk is a variable. It's a sequence. K equal to 1 to infinity or whatever. Is just Xn. Okay, but this Xn goes to 0. See, you take a element in the pre-dual and act this as this L1 is a linear functional acting on C0. Okay, and the linear functional is just summation. You recall this. If you have a Xn in C0 and Yn in L1, okay, the linear functional phi of Yn acting on this Xn is nothing but summation Yn Xn. Okay, this is the linear function. So if you take this coordinate function En, which is in L1, and if it acts on the C0, some C0 sequence, some sequence converging to 0, then En acting on the Xk is just Xn. But Xn is a sequence converging to 0 by its very definition. So it goes to 0. So this implies En goes to 0. Sorry, En goes to 0 in weak star topology. This is precisely the definition of weak star convergence. Okay. But if some Xk is contained in L infinity, okay, then now phi Xk acts on En, phi Xk acting on En is again Xn, okay, which need not converge to 0. It's just a bounded sequence which need not converge to 0. Okay. So En does not converge to 0 in weak topology. Not just that, you can see that it will not have any subsequence. I mean, there is no difference. I mean, it is just the evaluation function at the nth coordinate. So it does not have any subsequence which converges to converging weakly to 0. So the unit ball in L1 is not weakly compact. It is only weak star compact. That's what this shows. Okay. So by now, if you have any doubt, you tell me. I have just explained everything. Maybe I have not written clearly, but it's very easy exercise. You can do it yourself. So please get convinced. Okay. Any question? Okay. So let me give some more example. You take the same coordinate function in En contained in LP for P greater than 1, less than infinity. Okay. Of course, LP for P greater than 1, strictly greater than 1, it's all reflexive spaces. The dual of LP is LQ, where 1 by P plus 1 by Q is equal to 1. And the dual of LQ is again LP. So because of this, I mean, the weak topology, weak star topology coincides. Okay. Then En converges to 0 weakly. I mean, there is no difference between weak topology and weak star topology because they are reflexive. Okay. So En goes to 0 in weak topology. So this is true for okay. So the same thing I mean, this is true for L2 also, but we can prove it for a more general Hilbert space. This is, so you can do it in non-separable Hilbert space also, but separable Hilbert space, we can consider sequence. Non-separable means you have to consider nets. So I will better do it with separable Hilbert space. So let H be a separable Hilbert space. Hilbert space, and En be any orthonormal basis. Okay. Then En converges to 0 weakly. I mean, what do you have to do? You have to verify that En x for any x in H. Okay. But this goes to 0. But then x is equal to summation x En. There is this expansion like this. Okay. So it expands like this, and we know that in a Hilbert space, summation mod xen square is smaller than infinity. So this implies xen goes to 0 in particular. Okay. So this is how all linear functionals are acting on a Hilbert space. So because of this, any orthonormal basis will converge to 0 weakly. But norm En equal to 1. So En cannot converge to 0 in norm. Okay. I mean, all of them have norm 1. It cannot converge to 0. So En does not converge to 0 in norm. Okay. Okay. So what else? Okay, let me give some assignment now. So these are all assignments. The first assignment is so if phi n converges to phi in weak star topology, okay, then norm phi is less than or equal to lim min of norm phi n. Okay. This is very easy. You just have to write down the definition if you come. Then to if X is non-linear space and separable, it's a separable non-linear space. Non-linear space. Then the unit ball of X star is weak star metrizable. That is, the unit ball is metrizable. There exists a metric on the unit ball, not on the whole of X star, on the unit ball, which gives the, I mean, which generates the topology, which is same as the weak star topology. So maybe I'll give you the hint, not the hint, how to follow. So let Xn be is dense. You have a countable dense subset because it's separable. Okay, then you define d of phi and phi to be summation n equal to 1 to infinity d of phi of xn. It is just mod of that, or but then this will not converge, so you have to put a 1 by 2. I think this will work. Okay. So show that this is a metric, and this gives the convergence in the big star topology same as converging in this topology. Show this. Okay. Third one. So this in particular says following. I mean this. So this is not part of assignment. This is clear. This says that so this says that the unit ball is big star compact, which is in the metric space. So in particular, the unit ball is separable. Okay, but then you can write the whole big the X star as countable union of balls. I mean, this is not just for unit ball. For any ball, this is true. Any bounded ball, it's true. So this implies X star is separable. Weak star separable. Sorry, not separable. I mean, if X star is separable, then X is separable. But X separable does not mean X star is separable. Okay. But if X is separable, then X star is weak star separable. In particular, this L infinity, which is not a separable Banach space, is weak star separable. Okay. L infinity is weak star separable. It follows from these things. Okay. 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 So then the third one is, see, L infinity, L1 is separable. So L infinity is weak star separable. But then L infinity star is not even weak star separable. You can see by the following reasoning. We notice that the coordinate functions, the coordinate sequence En in L1 converges weak star in weak star topology, but it does not converge in weak topology. Okay, you can take the same coordinate function in L infinity. Yeah. No. See, the thing is, you have this coordinate functions in L1, which acts as linear functional. I mean, in the pre-dual, it's a pre-dual linear functional acting on linear functions on L infinity. I mean, L infinity is dual of L1, but L1 also acts as L1 is contained in the dual of L infinity anyway. So these coordinate functions can act on L infinity, okay, which is just evaluation on the nth place. And that gives a linear function, which is contained in the unit ball of L infinity star. But that will not have a weak star convergent subsequence. Okay, so this is the following which I want to say. Okay, consider let x equal to L infinity. Okay, then phi n. This is actually given, which is the point is, the funny thing is, this is actually given by L1, this phi n. Phi n from L infinity to C, which is just xn. If you have a xk, a sequence, k equal to 1 to infinity, going to xn, the number xn, the nth place, whatever that number. This is a linear function. Okay. Okay. Then this phi n does not have any convergent subsequence. Phi n does not have any convergent subsequence. Just verify this. It's easy, direct verification. Okay. Does not have any convergent subsequence. Is my handwriting okay? I mean, I'm somehow still not able to write it in iPad. My handwriting is always very bad, but when I write it in the iPad, it's very bad, very, very bad. So phi n does not have any convergent subsequence. So this implies, so norm phi n equal to 1. You can see that norm phi n equal to 1. Okay, so it is, so this implies that the unit ball of, unit ball of L infinity star is not metrizable. Okay, which indeed implies that L infinity star is not separable. I mean, if it is separable, it should be metrizable. Okay, so these are all, it follows immediately. All these things follow very immediately. Okay. Then the fourth assignment. So let's take a Hilbert space. Let H be a Hilbert space. En, we always take separable Hilbert space. En is an orthonormal basis. Okay. Then a sequence well, you can make it a little bit difficult. See, I can okay, a sequence xn is weakly convergent. Okay, is equivalent to saying 1 norm xn, supremum of norm xn is infinity, less than infinity, 2 xn ek goes to 0 for all k. No, sorry. Xn so converges. Maybe I should write it in n. Exists for all k. The thing is, the assignment can be it will be very easy if I say that xn converges to some x. If supremum xn is less than infinity, and the limit of, the limit of xn ek equal to x ek. If I say that, that's very easy. Here I am saying something slightly more slightly complicated. That is, if something is weakly convergent, then this happens. Okay, so you have to think a little bit. I am only assuming the limit exists here. Okay, so if the limit exists, then you can take that limit and you will find a linear functional, and corresponding to the linear functional, you will find an element in the Hilbert space, and that will, the limit will define a linear functional. Okay, using that on on all ek, and show that it is actually, its inner product with ek should be summable. So what you have to do is the following. You can define a linear functional on ek. You can define a x. You get something like this, x ek. Okay, and this x ek is summable. Okay, you are not getting this x. You have to get a x. You have to get numbers, this limit, and you have to show that that limit is summable. You get a limit of these things. For each k, you will get a limit, and that limit is square summable. So that will define an element in the Hilbert space. Sorry, there's no need for linear function. That will define an element in the Hilbert space. Okay, and that element is precisely the weak limit of this. Okay, I hope it's clear. But anyway, you think about it, you work it out. So this is an assignment. Okay, and if I give you the limit explicitly, then it's very easy. Then it's direct. So you have to work a little bit to get the proof. Okay, so these are the 4 assignments. Okay. Now let us discuss something more on continuity, weak continuity and norm continuity, something connecting these 2 things. So this is the following proposition. X is a non-linear space. Okay, so I can put different topology on this. So I write it like this. X norm means I have the norm topology. Okay, so T from X norm to X norm, a linear operator. It's just, I'm assuming only linear operator is continuous. So this is continuous with respect to the norm topology. You put norm topology on both the places. You can actually take Y. There is nothing wrong, nothing specific about X or something. X, Y are non-linear space. Okay. Okay. And you have a linear operator from X with norm topology and Y with some other norm topology, and it is a continuous operator. Okay. This is equivalent to saying T from X weak topology, okay, to X with weak topology. Okay, something quite nice. If you replace the weak topology with norm topology on the range side, it will not work. If you put weak topology on both the places, then it will work. Okay, proof. So why is this true? So proof. Okay, so let's assume that T from X norm to is continuous. Okay. So this implies if you have a bounded operator, if you have a continuous operator, linear operator, then we have seen between 2 Banach space, then we know that there is a adjoint to that, corresponding to that. Okay, this is true for Hilbert space, and we have proved it for Banach space also. Y star to X star. Okay, a bounded operator with respect to norm. Okay. It's adjoint. There exists something like this. So this is also continuous operator with respect to norm. There we are not considering any other topology, only the norm topology and y star and x star. So I have just written it like this. Okay, so there exists, this implies there exists a T star, a linear bounded linear operator between the corresponding, from y star to x star. Okay, now suppose, so what I have to prove? I want to prove that this is weakly continuous. This map is weakly continuous. So suppose some net, we have to consider net, but this is exactly like sequence. Okay, there is really, I will just write this lambda or something, but it is, you can consider this a sequence of x lambda converging to 0, x lambda converging to x. Okay, if you have a net, but we have to take net. Okay? Suppose x lambda converges to some net converging to x. Okay, then what happens? So converging to this in weak topology, that is phi of x lambda converging to phi of x. Okay, for all phi. Okay, now what do you have to do? Yeah, now I have to prove that T of x lambda, I have to prove that T of x lambda converges to T of x. That's what I have to prove in weak topology. Okay, so to prove that in weak topology, I take phi of this. So this is for phi in x star, phi in x star. Okay, now you have take phi in y star. Okay, phi of T of x lambda. I want to show that this converges to phi of Tx. That's what I want to show. I want to prove that I assume the norm continuity, norm continuity. When you put norm in the domain, norm in the range, norm topology, then the T is continuous. Then I want to prove if you put weak topology in the domain and weak topology in the range, then also it is continuous. So I have to prove that if x lambda converges to x weakly, Tx lambda converges to Tx, assuming the norm continuity of T. Okay, so I've assumed x lambda converges to x weakly. Then I have to prove that Tx lambda converges to Tx weakly. So I am taking the linear function phi of Tx lambda. I have to prove that this converge to phi of Tx. So, but then this is equal to Tx lambda. This is equal to T star of phi acting on x lambda, right? Where T star of phi, this is in x star. Okay, now this goes to T star of phi at x, right? Because that's what it's given. Okay, because of weak convergence of x lambda converging. T star phi is a linear functional on x. Okay, that is how the T star map is defined from y star to x star. Phi is in y star. So T star phi is in x star. Okay, this converging to x. Okay, but then this is equal to phi of Tx. Okay, so this implies phi of T of x lambda converges to phi of Tx. So Tx lambda converges to Tx weakly. So we have proved that norm convergence implies weak convergence. Okay. Now to prove the other way. Now suppose T is from X weak topology to Y with weak topology is continuous. We have to prove it's continuous in the norm topology. So one thing you should remember is, I didn't say weak topology, norm topology is stronger than weak topology. When you have a stronger topology, convergence in the stronger topology will imply the convergence in the weaker topology. Okay, that is just clear. We have to produce a open set. If we can produce in what you have to prove, why is this true? If Tx something converges to something, that what does it mean? Given epsilon or something, you have to produce a open set. Okay, so if you can produce in if you can produce it in what is the right thing? If something x lambda converges in the bigger one, then it is converges in the weaker. No, it's not the, it's the other way. Sorry. What is the right argument? Given epsilon, there exists a neighborhood such that No, you have to produce a neighborhood such that this is smaller than epsilon, right? That is the convergence of the sequence. Okay. So if you can produce it in a weaker topology, then you can produce it in a bigger topology because this is contained in that. So so anyway, where you verify this, okay? Suppose xn converges to x in norm. Okay, the stronger topology is write down the definition, it will be okay. Okay, then xn converges to x in the weak topology. Okay, but since we have assumed t to be weak convergence, txn converges to x in the weak topology. Now we have to prove that txn actually converges to tx in the weak topology. Now we have to prove that txn actually converges in the norm topology. But then we don't have to prove it. We want to verify that T is bounded. For that, we use closed graph theorem. Okay. To apply closed graph theorem, So what do you have to do? If you want to check an operator is bounded, it is enough to check that it's on a Banach space. Okay. We are using, I didn't say, did I say non-linear space? I will take it Banach space. Sorry. Because we have to apply closed graph theorem. So to apply closed graph theorem, so suppose xn converges to x, txn converges to y, then we have to verify that in norm, this is in norm, then we have to verify that this y is equal to tx. But then since, if txn converges to y, then txn converges to y in weak also. Txn converges to y, this implies txn converges to y weakly. This implies y equal to tx because the limit is unique in the weak topology. See the weak topology, so maybe I didn't say that, I will write it here. Weak topology is a Hausdorff topology. You know what is Hausdorff topology? That is limit is unique. That is given x1, x2, there exists linear functional phi such that phi of x1 is not equal to phi of x2. Okay. This implies if you use the neighborhood, whatever the neighborhood I have said, the way I have defined the neighborhood, oh shit. Time I was checking something else. So this implies there exists neighborhood. There exists u1, u2, such that x1 is in u1, x2 is in u2, and u1 intersection u2 is empty. Okay. And that's what Hausdorff means. The topology is Hausdorff topology. So Hausdorff topology implies the limit is unique. Implies limit is unique. Okay. So because of this, if txn converges to y, then y should be equal to tx. So by closed graph theorem, this is norm continuous. So and the theorem is proved and the proposition is proved. So I give assignment, this assignment, that is t is from some x with respect to norm topology. X with respect to weak, x or y, doesn't matter. Is continuous is equivalent to t from x to weak No, norm. There is no, it's not going to be weak. It's continuous. Okay, please do this. The same idea, closed graph theorem or something, and it will work. One of them will follow immediately. I think the other one of the you have to use closed graph theorem. So please do this. Okay. So, but then it is not true that this is not true. What is not true is the following. That day I worked it out and it's still there. I don't know. But this is not true. But this is over. What is not true is t from norm x with norm continuous is not equivalent to, does not imply. Other way is true, of course. This way is true, but this way is not true. T from x with weak x with norm. This is not implied. So wherever this property is satisfied, that is what is called compact operator. Okay, that is what we will see now. And compact operator can be defined for general Banach space, but since we want to prove some special theorem called spectral theorem, we will do it for Hilbert spaces. Okay, so we want to do what is called compact operators. For that, before defining compact operator, I want to define what is called finite rank operators. So from here onwards, let H be a Hilbert space. Okay. And if T from H, let us take H itself, okay, is finite rank, as you know, if T of H is finite dimensional. Okay. And let's denote all finite rank operators. So suppose if we have one operator, one finite rank operators, okay, then if you multiply with any operator, that's again finite rank. Okay. Multiply on the left or right doesn't matter. It's finite rank. So if S is a finite rank operator and T is in P of H, okay, then TS, okay, TS of H equal to S is finite rank, so S of H is finite. This is finite dimension. So T of some finite dimensional subspace is finite dimension. Okay, is finite dimension, right? If you have any linear operator, it will take a finite dimensional subspace to another finite dimensional subspace. So this is finite dimensional. On the other hand, ST of H, but then this is something, this is contained in S of H. Okay, so this is finite dimension. So this implies TS, ST are finite rank operators. So that is this FH contained in B of H is a two-sided ideal. Okay. Sorry about it. Okay. So what else is there about finite rank operators? And it's not just two-sided ideal, it's also what is called a star ideal. So if T from H to H is finite rank. Okay. Then H is equal to, I mean, you can take the range as K also, then also it will work. Maybe, I mean, the whole thing can be defined, but we are going to deal these things on a single Hilbert space, one Hilbert space to Hilbert space, one Hilbert space onto itself. Okay. So then this is going to be kernel of T. Any Hilbert space can be written like this: kernel of T star, direct sum, range of T. This is true. I mean, this is something I think Shruti proved before polar decomposition. Okay, kernel of T star is equal to range of T per. This is true for any T. I think she proved. If I think she proved it, but anyway, this is very easy to verify. Okay, kernel of T star. This is true for, I mean, general, any operator you can do. Kernel of T star is range of T per. But then since it is finite dimensional, this will imply that kernel of T star per will be equal to range of T closure. Okay. But then since it is finite dimensional, range is already closed. Any finite dimensional subspace is closed. So because of that, H is equal to kernel of T star plus range of T, which is a closed subspace. Okay. Now, if you take T star acting on H, which is equal to, on kernel of T star is 0, of course. That's the definition of kernel. So this is equal to T star acting on range of T. But range of T is finite dimensional. Okay. So T star acting on a finite dimensional subspace is finite dimensional. Okay. This implies T star is also finite dimensional. So if T is finite rank operator, then T star is also finite rank operator. Okay. So these things say that FH is, this is what is called star ideal, two-sided star ideal. I mean, that is, if T is there, T star is also there. And it's an ideal. If S is there, then ST is there for all operators. Okay. So how much time I have? I have only 6 minutes. So we want to deal with something called compact operators. This compact operator is what is called, it is just the closure of this norm with respect to norm closure. Okay. This is what is called compact operators. Compact operators is just the norm closure of finite rank operator. That means there exists a sequence of finite rank operators converging to compact operators. The point is, in finite dimensional, we have something called spectral theorem, which says that any matrix can be diagonalized. I mean, not any matrix, any normal matrix can be diagonalized. Okay. So here, it should be true for any finite rank operator, and that is true for any compact operator also. It can be diagonalized, means there exists a orthonormal basis, and it can be written as a diagonal operator with respect to that orthonormal basis. This is not true in general for any normal operator. For that, you have to do some direct integral or something. It's not, I mean, it's not an eigenvalue decomposition. Here it will be an eigenvalue. We will define all those things. Eigenvalue decomposition. So this is compact operator. So since I don't have time, I will not prove anything about compact operator today, but I will say something about this finite rank operator. This finite rank operator is a nice, see, there is another topology. If we take the closure of finite rank operator, that gives compact operator. Since all operators are not compact operator, which we will see, this compact operator is a subspace of all operators, all bounded operators. Of course, when it is infinite dimensional. In finite dimensional, everything is same. So it does not give all operators. But if you take a different topology, not norm topology, called a strong topology, then the finite rank operators, the closure of finite rank operators is everything. So that's what I will show now. So this, I think we have already seen. There is something called strong topology definition. Strong topology. on B of H. So we say Tn, a sequence of operators in B of H. Tn converges to T strongly if it converges pointwise, okay, for all x in H. That's all. Okay. So this is a well-defined topology you have to prove. I mean, we can define a topology by defining the convergence, then that will define the closed set, and that will give you a topology. That's not the problem. But if so, this is something you have to prove. I don't want to give it as an assignment, but this is, I don't know whether it was given or we discussed it. I think Nirupama gave it as an exercise. So if Tn converges to T, I mean, if Tn converges, what I want to say is, if Tnx converges for all x in H, just converges, okay? You can define T equal to limit of Tnx, okay? Tx equal to this. Then T is bounded. This follows from uniform boundedness principle. Okay, I think we have seen. T is a bounded operator. If pointwise limit of operators, sequence of operators, is a bounded operator. Okay, this follows from uniform boundedness principle. So because of this, the strong topology is well defined. Okay, this is strong topology. Now I want to prove the following proposition, that if you take the finite rank operators on H, the closure with respect to strong topology equal to B of H. To prove this, I need the following lemma. I mean, we always assume H is separable. Okay, if I don't say it, please assume it. Okay, H is separable. Okay. Then there exists sequence of projections, Pn, okay, projections, finite rank projections. Projections such that Pnx, I mean, it converges strongly to identity. Okay. Identity. This is just easy. If you have any x in H and choose any orthonormal basis, En, okay, then Pn be a projection from H to span of E1 up to En. Then Pn of x equal to summation k equal to 1 to n x ek ek, right? Any x can be written as any x equal to x will look like this, summation x ek ek k equal to 1 to infinity. If you apply this projection n, you will get only first n terms, n of them. Okay, this clearly converges to pointwise. This will converge to k equal to 1 to infinity x ek ek. This is equal to x. So this implies P and x converging to x. I mean, that is Pn converges to 1 strongly, okay, in strong topology. Okay. Okay. That is Pn converges to 1 strongly. Okay. Now, to prove this proposition, for any T in B of H, P and T is finite rank. Okay, if you are, I mean, Pn's are finite rank projections. So if you multiply by T, it's finite rank projections. Okay, now P and T converge to T strongly. Verify this. That is just clear, no? P and Tx converges to Tx for all x in H by definition. Because of that, P and Tx converges to Tx. So this implies that the closure of strong topology is everything when you take the strong topology. But this is not true for norm topology. Okay. Okay. So in the next class, we will discuss more on compact operators. Any questions? I stop.